Hello students, welcome to the series of lectures on linear integrated circuits and applications. So in this video I am going to explain about the second order active low pass filter. So in the previous video we have already seen what is a filter. So mainly we have already seen the first order active low pass filter and the analysis part, and also we have already analyzed the circuit of the first order active low pass filter. So in this video I am going to explain about the second order active low pass filter. So let's get started. Alright, so these are the two important objectives of the today's video. One is understand the op-amp based active filters, and you'll be able to analyze the operation of the second order active low pass filter. So this is the pin diagram of IC741. So I hope you understand why I'm putting each and every video. This slide is very important for us. Alright, so this part we already completed in the previous video. So what is a filter and how we have already analyzed the circuit. So please go through this. So this is a simple passive circuit of the low pass. So this is the analysis part of the filter. So this is a frequency response. So one point you need to understand from this slide is that when you want to draw the frequency response plot with respect to the frequency and the voltage gain. So for certain frequencies the graph should be flat. Okay, that means what you need to understand here is that so we are going to be allowing some frequencies, that to low frequency. The low frequency components we are allowing into the filter. So that I am calling as a pass band. So pass band is a band where all the low frequency components will allows, and the stop band is a band where all the higher order frequencies will be eliminated. Okay. So coming to our discussion of today's video, second order active low pass filter. So the first point I have mentioned here in this slide is that we are calling this as a voltage controlled voltage source. So let me take the pen. Alright. So we are calling this as a VCVS filter. VCVS is nothing but voltage controlled voltage source. Okay. Why we are calling? Because the operation amplifier that you are using in the designing of filter is a voltage controlled voltage source amplifier. Okay, that is the first point you need to understand. And the second important point from the slide is that so most designs of the second order filters, which are generally named after their inventor, with the most common filter types are Butterworth and Chebyshev, Bessel and Salenky. Okay, so these are the four important categories of the filter we are studying. But as far as our syllabus is concerned, we are only restricted to study the filters which are suitable for the audio frequency application. When it comes to the audio frequency applications, and definitely we should use the Butterworth filter is the best filter for all audio filters. Okay, so this point is very important because you are going to be designing the audio filters only, right? So for all audio filters, we are going to be considering the category is Butterworth. For higher order filters, we are going for the Chebyshev, Bessel or Salenky according to the application of the design. Okay, next. So this point is very important for us because when you want to design the second order active low pass filter, we normally see the slope. So okay, this is the low pass filter frequency response I am drawing. So this is we already know, right? So up to this, which is a plot, and here you will be having the higher cutoff frequency. And if you want to calculate the slope, so the slope could be for second order, which is minus 40 dB per decade. Please understand. Okay. For the first order, the slope could be minus 20 dB per decade, but for the second order, the slope could be minus 40. So what could be the reason? So the reason maybe here is you are going to be using two RC pairs. Okay. So one single RC pair will be giving you minus 20 dB per decade. Because this is the second order, we are going to be increasing the pole of a system. So one more pole is going to be adding here. So therefore, we will be having the slope could be minus 40 dB per decade. Alright, so this is the circuit of the second order active low pass filter. Okay, so you can see that. So this is one pole. R1C1 is acting as a one pole, and another R2C2 is also we have given. So this is the another pole. So total how many poles we will be seeing? Two poles. Okay, so that decides what is the order of the filter. So the order of the filter is a 2 now. Okay, Now let us see the analysis part. So before we see the analysis part of this circuit, so this is the non-inverting operation amplifier. That is the first identification we are going to be doing with respect to the circuit, because we have given input to the non-inverting input terminal. Obviously the gain is also very well known to us. The gain should be 1 plus Rf by R1. Okay, and if you want to calculate the cutoff frequency or the 3 dB frequency, so the 3 dB frequency for the different values of the resistance and capacitors could be Fc equal to 1 upon 2 pi under root of R1 R2 and C1 C2. Okay, but if you take the equal resistance values and if you take the equal capacitor values, you will be getting Fc equal to 1 upon 2 pi into Rc. Okay, so these formulas are also very important if you want to do the examples. Okay, if you want to design any example for second order active low pass filter, so please keep that in mind. So these are the formulas you need to be applied. Alright, now let us see the analysis part. Okay, so I am drawing the circuit because if you want to do the analysis, so this is the circuit we are going to be considering. So please see carefully here. This is minus and this is plus. So here you will be having the resistance, and this is the feedback resistance. This is Rf and this is R1. And here, instead of taking resistances and capacitors, I am going to be considering admittances, because our analysis will be simple if you take admittances in place of resistance and capacitor. Okay, so that we can witness after completing the derivation. So this is Y1 and Y2 I am giving here, and the other admittance I am taking from here, that is Y3, should be given to the output voltage, and one more admittance, that is Y4, which is connected to ground. So here I am applying the input voltage. Alright, so this is the circuit diagram. So whatever the circuit diagram that you already seen in the previous slide, which is same here, but only the difference is that here we are taking the admittances. This is for our simple analysis only we are considering. Okay, so here Y1 is equals to Y2. So this circuit behaves like a second order active low pass filter if and only if you consider Y1 equal to Y2 is equals to 1 by R and Y3 is equals to Y4 is equals to SC. That is the condition we need to consider. Okay, so this is an amplifier of a op-amp. Okay, now let us start the discussion with respect to the analysis part of this filter. So here I am taking as node A, this is node B, and see the direction of the currents. So this is the direction of the currents I am going to be considering. Okay, so to do the analysis, first we need to apply KCL at a node capital A. Okay, so if you apply KCL at node A, what will happen? So now we need to identify how many number of currents which are entering to the node and how many currents which are leaving from that node. Okay, that you need to identify. So obviously it is very clear that from the circuit, so at node A only one current which is entering and the two currents which are leaving. Okay, so please see carefully how I am writing the equation. This is Vi minus Va into Y1. This is the current which is entering to the node. Okay, is equals to, and the leaving currents are 2. Okay, that is the summation I am considering. So how many number of currents which are leaving? One is Va minus V0 into Y3 plus Va minus Vb into Y2. Okay, so this is the first current. Okay, this is the second current, this is the third current. One current is entering and two currents are leaving. So you can also rearrange this equation, that is Vi into Y1 if I take in the left hand side, and if I send Va to the right hand side of the equation, you will be getting what? And if you common Va, this is Y1 plus Y2 plus Y3. Okay, and what is the rest of the terms we will be having in the right hand side of the equation? We will be having minus V0 into Y3 and we will be having minus Vb into Y2. Okay, so you name this equation as 1. And one more point we should observe here. As I already told you, this is the non-inverting operational amplifier. So for non-inverting operational amplifier, what is the gain? or what is the output voltage, we can directly consider V0 is equals to 1 plus Rf by R1. So this can be holds good if you assume operational amplifier is ideal. Okay, otherwise you don't use this expression. Okay, so V0 equal to 1 plus Rf by R1 times of input. What is input here? VB only, because of the virtual short. Okay, so this is VB. So from this, what I am writing here is that I am considering this with the passband gain as A0. Okay, so directly VB is equals to, can I write V0 by A0? Okay, so this is the final expression we will be getting for VB. Okay, now you substitute VB in the equation 1. Okay, so let me go to the next slide. So we have got this expression, Vi into Y1 is equals to Va into Y1 plus Y2 plus Y3. Let me go back, and minus V0 into Y3 and minus VB into Y0. So in place of VB, what I can write? V0 by A0 into Y2. So this is the equation number 2. Okay. Next, so we are going to be applying KCL at another node. What is the another node? Node B. So if you apply at node B, so see the circuit and tell. So you will be having only one current is entering, right? That is VA minus VB into Y2 is equals to VB into Y4. Okay. The same thing I am writing. VA minus VB into Y2 is equals to VB into Y4. So here if you send VB to the right hand side, you will be getting what? VA into Y2 equal to, if you common VB, Y2 plus Y4. But in place of VB, we can also write what? V0 by A0 into Y2 plus Y4 whole divided by Y2, which is VA. That's all. This is equation number 3. Okay, now you need to substitute equation 3 in equation 2. So we get the final expression I am writing, that you verify what is the expression that you are getting. So finally we got V0 by Vi is equals to Y1 Y2 into A0 by Y1 Y2 plus Y2 Y3 into 1 minus A0 plus Y4 into Y1 plus Y2 plus, right? That's all. Okay, but here what is Y1 and Y2? We need to substitute, that is 1 by R. And what is Y3 and Y4? SC. Okay, so if you substitute this in the above equation, so you will be getting the final expression in terms of S domain. V0 of S by Va of S is equals to, which is A0 by 1 plus SCR into 3 minus A0 plus SCR whole square. So this is the final expression we will be getting. Okay, so I hope you have understood how we have analyzed the second order active low pass filter. So this is the quadratic expression that you are seeing in the denominator. Okay, thank you students, thank you for listening to this lecture.